So to open our lecture today, which is lecture 4 of this class, I'm going to share you a question I got asked by my graduate student, which is this question 7. I guess he was asked by an undergrad student. So you can take a look and let me know what you think is the correct answer. Maybe we can read this question together. The least squares estimate of the slope. So I think this question is about the simple linear model where you have only one numerical or continuous predictor in your linear model. The least square estimate of the slope is not exactly equal to the true value of the slope, or at least there is a very large probability that these two are not equal. Which of the following helps us measure how far away an estimate of the slope might be from the true value? Okay, there are several answers: the t-statistic, the correlation coefficient, the p-value, the mean of the least squares estimator of the slope, the variance or standard deviation of the least squares estimator of the slope. So for those of you who are willing to speak, please just unmute yourself and try to explain what you think is the correct answer and why.
Is it E, the variance of the estimator of the slope?
Yes, actually the answer is right here, so you can look it up here.
Oh,
But
that's
Nathan, yeah, are you willing to explain why you think E was the correct answer? I was asked yesterday. Yeah, my
okay.
student just asked me, why isn't it the T statistic?
So I think so the variance of the least squares estimator is we're trying to estimate the sampling variation.
Mm-hmm.
So it gives us a sense of, in repeated estimates of the coefficient, how far apart they'll be.
Yeah.
Tells us how far it might be from the true coefficient.
Yeah, that's a very good answer. So I just want to make a small correction. That is, if you want to talk about the distance between your slope estimator from the true slope, you're actually talking about the mean squared error, which is the expected squared difference between the estimate and the true value. And we know that an MSE, mean squared estimate, mean squared error, that can be decomposed as two terms. One is the square of the bias, one is the variance. So they together will determine the MSE. And this equation, MSE equals bias square plus variance, is the fundamental rule of statistical machine learning, which means that if you fit a more complex model, you are essentially reducing the bias term, but you are inflating that variance term because a complex model is less stable in terms of parameter estimation than a simpler model. On the other hand, if you fit a simple model like a linear model, you have a large bias, which means that the expectation of the model may still be far away from the truth. That's what we mean the bias. The truth may be nonlinear, but you are trying to fit a linear model whose expectation is linear. But your variance is rather small since that it's a simpler model and the estimation of its parameters is rather stable. So that reflects that bias variance trade-off. But here in this answer, so it doesn't talk about the bias that much. It's focusing on the variance. The reason is that here, I think in the undergraduate level, when we teach the linear model, we are inherently assuming that the linear model is the truth. So we are not having the bias in our mind. In that case, the expectation of the of the of the estimator is just the true value. So you ignore the bias, and then the variance is the only term that's in the mean squared error. So that's why here variance reflects the how uncertain our estimated slope is from the true slope. Yeah. And then let's revisit t statistic. What is the t statistic about? Why is some student, or why is this student confused about t statistic? So in some way, we can say that the t-statistic is also measuring like the distance between your estimated slope and the true slope in some way. But here, the true slope is assumed to be the one in the null hypothesis, that is 0. So when you use t-statistic, you are essentially using your slope estimate to check, do I think the true slope is 0 or not? That's a hypothesis testing problem. So that's why it's not the thing you want to measure just for the variance. You are doing a test against true slope being 0. So that's why this answer does not apply here, or is incorrect here. So do we have questions from our students? Since this is a simple linear model, I hope that now we're all clear about this answer before we move on to our more advanced models. Okay, so that's it. And one more thing I want to share with you guys is about the lecture notes. As I said, I will do proofreading and fine-tuning and repost the updated notes every lecture so you can check out the updated version. But this original version from previous years subscribed by students is already on CCLE just for your preview purpose. I want to point out one thing which I realize is very common among our students writing with LaTeX. That is this. So you see this K predictors, first of all, this is a typo, it should be K levels. But this K predictor, if you take a closer look, you can see that it's not in the math font. Okay, so but you see here this I and this J, they are in the math font. So, and also here, if you go down, this I go from 1 to K is not in the math font. J go from 1 to NI. NI is in the math font, but those are not. So this is not a very professional way of writing LaTeX. Please make sure that in your text, even though this K is something you can write without a math font, but if it is a math symbol, please put it in the math font so to be consistent with yourself. And this is something you should pay attention to in your final project report if you're going to use LaTeX and if you're new to LaTeX. Another thing is that I can see this is not written in the math font. It's probably just 3 dots. But if you write in the math font, then 3 dots, you could do backslash L dots or backslash dots. That will give you the correct font. So those are little things to pay attention to, but it's very important. And one more thing I also realized is the inconsistency of the notations here. So here, the sample size, which is the number of observations, is n, which is consistent with our previous notes. But if we go down, when we are in this to Way Anova, which I will talk about today very soon. So you see this n is to use to represent the number of levels of factor 2. So if you are the student and you read this note from the beginning, so this notation switching may cause some interpretation issues. So that's why I'm going to make a correction for those. So for today, I'm going to say we have a capital I levels for factor 1, capital J levels for factor 2. So we're going to save this n for the number of observations or the sample size. So here, the capital N is as the sample size. I'm going to restore it back to this lowercase m. So you will not have that notation inconsistency in the notes. But I'm just trying to point it out so that for those of you who have read this notes already, you're not confused. Okay, so let's start our lecture. All right. So in the last lecture, we talked about the multiple linear regression, right? So we give you the ANOVA. It's another way of testing whether certain coefficients are 0. And it can be used, the ANOVA can be used as alternative to the wall test and the likelihood ratio test. And we talk about the hierarchical ANOVA. So one special thing about the hierarchical ANOVA is that what you are going to be interested is the F statistic, which is for the last predictor or feature you added to your model. It's about whether this additional predictor has a significant contribution to the model fitting given the existing features. Okay, so we basically have finished everything we want to say about for continuous predictors. And before we talk about the categorical predictors, one last recap from our last lecture is that we talk about the coefficient of determination, the R squared, and the partial correlation, which has a similar interpretation as our coefficient in a multiple linear regression, both of which are about the conditional contribution of a predictor given other predictors. But the key difference is that the coefficient is not scale-free, and the coefficient estimate as a result is not scale-free. If you scale your predictor, the coefficient will change accordingly. But the partial correlation is scale-free. So its computation can be done by this three-step thing. You first regress your response on the predictors not of your interest to obtain residuals. Second, you regress a particular predictor of your interest against other predictors to get the residuals. Finally, you compute the Pearson correlation between the two residual vectors. That's how you define the partial correlation between the response and that particular predictor. So one thing I want to say about this partial correlation is that it's often used for network analysis. So let's say you want to build a network with between variables. Let's say each node in my network is one variable, like y is one node, x1 is another node, x2 is another node. So for those nodes, if you want to draw an edge between two nodes, given that the two nodes have a non-zero partial correlation, you can do that. So what does it mean? It means that my edge in my network represents association between two variables given or conditional on the other variables in my network. So this kind of network construction is different from that marginal association. So you could imagine another way of doing that is you could just draw an edge between two variables if those two variables have a Pearson correlation greater than zero or much larger than zero. So there are two ways of doing that. So one is for marginal association, one is for conditional association. And for the conditional association network construction, another common way of doing that, you can probably learn from other classes here, is about so-called the Bayesian network, or people can just assume. So one simple way is to assume that the nodes are jointly multivariate Gaussian. If that's the case, then a way to construct those conditional association is to take that Gaussian covariance matrix, or you take the correlation matrix after standardization for the variances. You take that multivariate Gaussian correlation matrix, you take its inverse, call that the precision matrix. And in that precision matrix, if any two nodes have their corresponding entry not equal to zero, you draw an edge. And so under that multivariate Gaussian setting, you can actually find this partial correlation, whether it's zero or not, by looking up that precision matrix. So that's a very common practice at network construction. Okay, I just talked a little bit more beyond this partial correlation we presented last time. So you know it has very wide application because its interpretation is very good. However, one drawback of doing this network construction compared with marginal association is that your computational cost is so much higher. It's very easy to compute marginal correlation, but if you have a very large number of variables or features in the network or nodes in the network, then finding the partial correlation can be very time consuming. Okay, so now today we're going to move on to a new topic, which is what we call categorical predictors. So previously, all our discussion are concerning numerical or continuous predictors. So now let's look at categorical predictor. So let's think about a linear model with one categorical predictor. So by categorical, we mean that this predictor's labels are discrete, and also there's no, so it could be, you may have a specific ordering of the labels. For example, if the predictor has its education level, like you can have high school, undergraduate, or bachelor's, or postgraduate. So that those three levels have a natural ordering. So in that case, we call it just so in that case we call it an ordinal random variable. Let me see, is it ordinal or nominal? So there are two things. Can somebody correct me? So for the categorical variable with an order, is it nominal or ordinal? I saw someone is searching online.
If there's like an order to them, I think it's ordinal.
It's ordinal, yeah. And then the nominal means that there's no order. There's no order for that. Okay, so let me just give you one example. So categorical predictor has two types, ordinal or nominal. Okay, so for this one, maybe I can tell you, say the high school, college, graduate. This is one example, which is this predictor has three labels, but there's an order, so it's ordinal. But nominal means if I have some colors, right? Let's say yellow, red, blue. So for those labels, there's no natural order. You can order the levels. So that's what we call nominal. But regardless of regardless of which one we're going to use, it's a categorical predictor. It means that the labels are not coded as numbers, or you don't want to treat them as number. So for example, for the ordinal, so you can compare this. Okay, so ordinal with three levels. Think about how this is different from treating it as coding as 0, 1, 2. So if you treat this as a numerical predictor in a linear model, you're essentially assuming that the effect of this predictor when its value is 2 will be twice of its effect when its value is 1. So that's why you assume this linear relationship. But when you assume it to be an ordinal with three levels, you don't assume that the effect going from 0 to 1 is equal to the effect going from 1 to 2. You lose that assumption. So that's why this model actually gives you greater flexibility. Okay, so this is something just to keep in mind when you think of the use of categorical variable. Okay, now let's formalize our notation. So we assume that, let's do the notations. We assume that this predictor has capital I levels. And by the way, when we do a linear model with one categorical predictor, we have a name for it. So the name we use for this kind of model is called Way Anova. So you can see that in the statistics literature, ANOVA is used as a way to say linear model. It's just that for the previous ANOVA we talked about, the predictors are numerical or continuous. But here, this one-way ANOVA is specifically for saying, okay, you have only one predictor in your model, just like in your simple linear model, only one predictor. But here, the predictor is categorical instead of numerical. Okay, so the predictor has I levels, and we have Ni observations in level I. So if we divide our observations based on its level, their levels in this predictor, so we denote that Ni is the number of observations in level I. So in other words, our sample size, N, will be the summation of ni, with I go from 1 to I. Okay, and then we have the response. So the response, now we need two sub-indices, so I and j. I indicates the level this observation is in, and j is the index of the observation within this level. Okay, so this is the j response in level I. In other words, we can let j go from 1 to ni. So you see here, we need, with our y, it has two sub-indices instead of one as in the previous notation. So then, what is the random structure and what is the systematic structure? That's the two things we want to think clearly. The random structure is regarding the random response, how its distribution is like. Or let's think about the systematic structure first. Probably that's easier. In this case where we have I levels, so what we assume is that each level has its own mean. And then the random response observations within that level is distributed around that level mean. So in other words, we can think of the mean of level I is equal to some intercept mu, which is the common mean across all the levels, plus some offset, alpha I. So here I again go from 1 to capital I. That's the systematic structure. So in other words, you see, we are not assuming that there is a linear relationship between the predictor value and the response and the expected response. The reason we didn't assume that is the predictor is non-numerical. It just gives us I levels. So we cannot assume any relationship between the I levels. Rather, we assume each level to have its specific mean. Okay, so given the mean, the random structure is still Gaussian. Here we are still under the case where we assume the noise is Gaussian. Okay, then it's this sigma squared. That's the random structure, that's the systematic structure. And if you remember, compared with what we had before in the simple linear model, the difference over there is the mu I is different. So over there, we have the mu I written as beta 0, if you remember, plus beta 1 xi, right? So this xi is the numerical value of the ith observation in that predictor. We multiply it with a slope and we add it with the intercept. So here we still have the intercept mu, but here the effect is not encoded as a slope times the value because we do not have a specific value for level I. Instead, we just give every observation in this level I with the same offset from the intercept. Okay, so now one more thing to think about is whether this model is identifiable. This is a very important thing to consider when we define a model. Identifiable means that can two sets of parameter values give you the same model? If yes, then the model is not identifiable. So let's think of this. You can think of the systematic structure to see whether you can have different sets of parameter values that give you the same systematic structure. In fact, yes. Okay, so you can imagine that what I could do is I could subtract mu from both sides. So in other words, I could have those two ways of parameterization that give me the same model. So one is like mu I equals mu plus alpha I. That's our original writing. But now, if I do a subtraction of a constant from both sides, I could do mu I minus 1 equals to mu minus 1 plus, or maybe, sorry, let's keep it here. Mu I equals mu minus 1 plus alpha I plus 1. Yeah, this is better. So look at this. So mu is changed to mu minus 1. Alpha I is changed to alpha I plus 1. But their sum is still the same. So in other words, I have two sets of parameters that are different themselves, but they give me the same model. So which means that not identifiable, this model. So realizing this, I need to add a constraint to my model by removing one parameter. And the parameter I could remove, there are two choices. One is that I could just enforce the intercept to be 0. If I do that, then I cannot do this shifting, right? Because the intercept will stay at 0. Another possible way of adding a constraint is to constrain one of the alpha i's to be 0. And this is more common in practice. So I'm going to write this as the fix we're going to use here. Set alpha 1 to 0. In other words, you assume the first level, whichever you define, is going to be just the intercept. And for other levels, you assume the offset is in comparison with the first level. So with this, then we have parameters, right? So the parameters are what? The parameters are just the intercept mu, and alpha 1 is 0, so we can leave it out, starting with alpha 2 to alpha I. So in total, this parameter, we still use this column vector notation. This is I-dimensional, and we can give it a notation to be consistent with our previous context or notation. We can still call it beta. So now with this beta, we can actually have our design matrix, and we can still use our previous vector form to write the linear model. Okay, so let's take a look. How do we do it? This can reflect the systematic structure and the random structure. So the first thing we need is our y. And here the y is a little more complex than before because we have ni observation within level I, and we need to stack all the levels together. So here we would write our y as y1, 1, 2, y1, and 1. So these are the n1 observations in level 1, sorry. And then we would go down here. We would have y1i to y1ni. So this is the ni observation in level I. And finally, we have y, let me see, sorry, my bad. yi1 to yini. Yeah. Finally, we have yi1 to yini. So these are the ni observations in my last level. So I'm going to stack all of them together. And still, because n1 plus n2 plus 2ni equal to n, so the dimension is still n. It's still an n by 1 vector. That's the response. And now the design matrix is corresponding to the mean. So the design matrix, we know now it should be n by I. So n corresponds to n observations. The I corresponds to those I parameters. So we can basically encode each observation's predictor value based on these. So how does that look like? So let's realize that in this design matrix, the first column is the intercept. Okay, so this corresponds to the intercept, and every observation should have a value 1 in the intercept. So I'm just going to write this correspondingly. Okay, so we have a set of a column of ones. And now let's look at the second one is alpha 2, which means that we are directly jumping to level 2. Level 1 is left out. So for the first N1 observations, since they're in level 1, we don't need to worry about them anymore. So alpha 2 is just depending on which observations are in level 2. We are going to give them corresponding ones here. But since I didn't specify them here, we're going to skip level 2, but go to level I. You see, level I corresponds to the observations here. And these observations have an intercept as well as the offset in level I. So they will have 1 here, but other observations will all get 0 in this level I offset. Finally, level capital I. And for those ones, we only need to give ones to the observations in this level, which are the last ones. So others are all 0. So this is our design matrix. It's just an encoding of the predictor levels for each observation. So to summarize, for each observation, in this corresponding row, we're going to give it a 1 in the intercept column, and we're going to give it 1 in the column corresponding to its level. That's the design matrix. And beta, we have it, right? So it's corresponding to the columns in X, mu, alpha 2 to alpha I. Alpha, yeah. That would be my beta. So this is a I by 1. So finally, I would have an error term corresponding to the y's. So probably I can just write it simply, so you know what I mean. So it's just epsilon 1, 1 to epsilon 1, n1 to epsilon I1 to epsilon I, ni. So it's still I by 1, n by 1 corresponding to the errors. And here the epsilon ij's are assumed to be all IID normally distributed with the common variance, the same assumption as we have for the linear model with continuous predictors. So putting them together, you see that the linear model is still in the same form, y equals x beta plus epsilon. For this one-way categorical variable, we can still use the same matrix form. And here, if you really think about this design matrix, you can see that even though we are only including one predictor, but effectively this predictor is corresponding to I minus 1 predictors as I minus 1 continuous predictors. So let me write it here. So this one categorical predictor, okay, with I levels is essentially equivalent to I minus 1 continuous or numerical, maybe that's better, numerical. Essentially, this numerical is binary, numerical binary predictors. The reason I said it's binary is if you look at the columns here, you can see, think of this correspond to one predictor, another predictor, another predictor. Then for each predictor, our observations have only 0 or 1 values in that predictor. Okay, so then I have a question for you. So this is a very interesting question to think about. Suppose that I have a continuous random variable. In our data analysis, we could always do discretization. So let's say this is my continuous x or numerical x. This is my response y. Let's say that my scatter plot looks like this. Okay. if this is the scatter plot, which means that each dot is an observation, I'm just plotting the observation in this matrix. Oh, sorry, in this scatter plot, and then you can see that in this graph, then you can see that what I have two options. One is that I could fit a simple linear model, by treating X as numerical. Another option is I could discretize and then do one-way ANOVA. So by discretization, I mean that I could just, in this example, I could divide it into 3 bins. I could call this low, medium, high. And for each level, I could do one-way ANOVA. So you can see the difference in those two approaches. If I fit a simple linear model, then my fitted line will probably look like this. That will be my fitted values. But if I do one-way ANOVA, I could just fit a mean for, I would just fit a mean for each level. That will be the fitted values. Then comparing those two options, what's the difference here? Or maybe I can make the question simpler. Which model is simpler? Option 1 or option 2?
Wouldn't option 1 be simpler just because there's less parameters to fit?
You said left option 1 is simpler, right?
Yeah, because there's less parameters to fit.
Exactly. Yeah. That's the easiest way to figure out the complexity, by thinking of the number of parameters. That's correct. So if we think about the option 1, we only have 2 parameters. One is the intercept, one is the slope. But in option 2, we have 3 parameters. We have intercept at the offset of level 2 and the offset of level 3. So that's more complex. But if you think of the complexity and look at the data, then you can see that option 2 can probably help you fit the data better if your data is actually not linear. So for example, what if the data look like this? If I make it non-linear, like I have some data point here and some here and then some here. So if that's the data, then clearly if you fit a linear line, that would not be a good fit. It's not a linear pattern, but still that discretization and then fitted the mean, the one-way ANOVA, it can fit it better. So you can think of option 2. So complexity, let me write it here. If you think about from the number of parameters, then option 1 is less than option 2. And you can think of option 2 as the simplest way of doing nonlinear regression, okay? So option 2 is a naive or simple way of nonlinear regression, which is a central topic in non-parametric statistics. So, and you can think of this as the simplest linear interpolation. Oh, sorry, piecewise interpolation. But then we can actually make option 2 a little bit more complicated by saying, okay, within each window, we could fit a linear function or a polynomial function instead of just a mean intercept. Okay. So that's good. Then with this notation, okay, coming back to this matrix notation, we can carry over all the knowledge we have accumulated. So with this linear model, then basically beta hat is still the least square with the same formula. So this can still be this least square. And the variance of beta hat or covariance matrix of beta hat is still this one. So all the results we have learned before can be carried over to this one, including the t-test for one parameter, one single element in that data, the wall test for a subvector of data, the likelihood ratio test, and the ANOVA we talked about last time, all of them are still applicable. So that's why you see the benefit of using the matrix form. It can unify a lot of things. So we do not need to treat the one-way ANOVA specially and different from the continuous predictor case. And one more thing that's worth knowing is that for any linear model, the key is to think of the design matrix, to fill in the design matrix. Once you have the X determined, then all the analysis just carry over. So that's why in your homework, which I'm going to assign, I think tomorrow or today. So in the homework, you're going to basically, a lot of questions are concerning how to fill in the design matrix given the data you have, or given the data and given the model, both of which will determine the design matrix. Okay, so after saying this, we can also have that relationship, if you recall, which is the foundation of ANOVA, SST equals SSR plus SSE. Sum of square total, sum of square regression, and sum of squared error. And with this, then we can define a coefficient or correlation coefficient between that categorical predictor and the continuous y. That's why we call it the point by serial correlation. This is a quantity in the topic called categorical data analysis. So there are several good books about that. If this is something you're interested in, you can check it out, because you see here our predictor is categorical, right? So it belongs to the categorical data analysis, and one-way ANOVA belongs to this as well. So this point by serial correlation is defined based on this one-way ANOVA. So it's defined as, maybe I can call this point by serial correlation. It's just defined as SSR over SST. So it's very similar. It's just, or I should say, it's just the R square we are familiar with from linear model. And we can use this to define how much does a categorical predictor associate with a numerical response. And it belongs to 0 and 1. Okay, so that's one-way ANOVA. Now let's move on to two-way ANOVA. We have two categorical predictors, and it should be similar. Oh, sorry, one more thing I should say is about this estimator. I forgot to say about this. So in this estimator, once you have this, right, the fitted values, fitted response, we know it's still this y hat x beta hat, right? The same thing. But for this one-way ANOVA, we can actually write it out easily because the design matrix is so simple. So given that design matrix, all the columns are binary. So this can be simplified. And after the simplification, you would have this. So for the for the parameter, for the estimate beta hat after simplification, and you will be happy to see that it agrees with your naive estimate. Let's say you don't know this linear model at all. I just ask you to guess what will be the mu hat, the estimated slope, what will be the estimated offset. These are all very straightforward. So the mu hat, we know it's just the mean of level 1. So it would just be equal to y1 bar. So this y1 bar is defined as 1 over n1, j from 1 to n1, yij. So the average of the responses in level 1. And then the offset, alpha 2, it would just be equal to y2 dot bar minus y1 dot bar. So the difference between the average in level 2 minus the average in level 1, okay? And finally, alpha I hat. That's yi dot bar minus y1 dot bar. So these are the estimates we will guess if we don't know about the linear model. But happily, we can check that it will be just equal to this beta hat we calculated. We'll calculate, use this formula. Okay, that's all I want to say about one-way ANOVA. Now let's look at two-way ANOVA. Two-way ANOVA. And we call this, the case is the linear model with two categorical predictors. So in statistics, we call a categorical predictor as a factor. This is also the object name used in R. So in R, when we see a factor, it's actually a categorical predictor. Okay, so we're going to use name factors here. And to start with, we're not going to assume any interaction between the two factors. No interaction. So no interaction means that their effects are additive, which means that for each observation, its mean or its expectation is purely defined by the addition of the effect of factor 1 and the effect of factor 2. Okay, so factors 1 and 2 have an additive effect. Okay, so to simplify our discussion, let's still define the notations. So let's assume that factor 1 has I levels, factor 2 has j levels. So then each observation will have two-dimensional levels. One is the level of factor 1, one is the level of factor 2. And we see that we have Nij observations with level 1 in factor 1 and with level I in factor 1 and level j in factor 2. And we take the summation of Nij as our total number of observations. So it's I go from 1 to I, j go from 1 to capital J, Nij. So you see the reason I use this I and j to denote the number of levels instead of the ones in our previous notes is because here we can see a correspondence between the index lowercase I and the number of levels, the uppercase I. So you can see the connection more straightforwardly. Okay, then we need a third index for our response to indicate the observation within this levels I and j. So that would be our yijk. We need this third index. So this will be the kth observation in levels ij. I'm going to use this encoding. That means factor 1 has level I, factor 2 has level j. Okay, and we know that k go from 1 to nij. That's the number of observations I have in this levels ij. Okay, then the next thing to specify is the model. Again, we have two layers, the systematic structure and the random structure. The systematic structure is about the mean of yijk. So we did know that for observations within the same level ij to have the same mean, which we did know that's mu ij. So this is the expectation of yijk for all the k in 1 to nij. They share the same mean. And as I said, here we're assuming that the two factors have no interaction. So their effects on this mu ij are additive. We have a common intercept mu, and the effect of factor 1 in level I, and the effect of factor 2 on level j. I'll just use gamma to denote that effect. So they are additive. And the random structure is about how the observed random observation is distributed around its mean. So we assume yijk to be IID, and here the IID is about J, about K, IID in K, okay, from 1 to Nij. These Nij observations are IID. They are IID following the same mean, mu ij, and a common variance sigma square, which doesn't depend on I or J. That's the two-way ANOVA model. And by the same argument for identifiability, we cannot have all the parameters vary freely. We need to constrain some of them. So identifiability needs to be specified, needs to give constraint. And here the constraint I do is to set alpha 1 equals gamma 1 equal to 0. So for both factors, I specify their level 1 effect to be 0. So when they are both in level 1, I would only have the mu, the intercept, as the expectation. Okay, so then you can see that will be the model. And then what's the parameter? The parameters can be specified by writing out the parameters we can allow to vary freely, which is mu, starting from mu, then let factor 1's offset alpha 2 to alpha I, and factor 2's offsets gamma 2 to gamma j. Okay, so what's the dimension here? If we call this beta, then we have 1 plus I minus 1 plus j minus 1. So it's actually equal to I plus j minus 1. That's the number of parameters I have in this model. So then, as we said for one-way ANOVA, if we want to use that matrix form for this linear model, what's left is to specify the design matrix, okay? And because the design matrix will have rows corresponding to the observations in our y vector, so let's first write down the y vector. How are we going to stack our data? Okay, so here, we first want to stack all the level 1s. So if we write it out, we will have y1, 1, 1. That's the first observation in level 1 and 1 for factors 1 and 2. So let's keep that 1, 1, and 1, 1. Okay, that's the number of the observations. Then let's move on to level 2 in factor 2, but keeping factor 1 as 1, level 1. So we have y1, 2, 1 to y1, 2, and 1, 2. And let's continue. So finally, with level 1, factor 1 stay as level 1, our factor 2 can go to j, y1, j, and 1j. Okay, after so many observations, we have used up all the observations whose factor 1 is level 1. So now let's repeat all of those and go to when factor 1 is in level I. So we have y1, yi1, 1, 2, yi1, and i1. Okay, so these are the observations with level I1. And finally, yij1 to yij and ij. That will be our observations. So it's a very long vector. So you can see we're taking n11 observation, n12, 2, n1j. Okay, and here we have ni1, 2, nij. So corresponding to this, you need to write your design matrix accordingly. So maybe I can make this smaller and you can see this better. So then the corresponding design matrix, I'm going to write it out. So I still call this an n-dimensional vector because that's how we define n. And this is going to be n by I plus j minus 1. And here in the design matrix, the columns will correspond to our parameters. So the first column is mu. And then we have alpha 2 to alpha I. And then we have gamma 2 to gamma j. So how are we going to fill out this design matrix? The simple way to do it is to look at each observation and find its corresponding encoding in terms of factor 1 and factor 2. So let's look at the first n11 observations. So they are just in factor 1 level 1, factor 2 level 1. So they only have the intercept. So we just give them 1 in the intercept. And by the way, so everything here in this column will have 1. So intercept has we have nothing to change. It's just 1 everywhere. Okay, so these, and we're done. So all the remaining things are 0 for these observations. And for the second one, you see, level 1, factor 1 is level 1. We don't need to worry about. But factor 2 is level 2. So we need to give them 1 here. That's for these observations. And for these ones, their factor 2 is level j. So we need to give them 1 here. And that's it. Okay, and then we move down. So for those ones, their factor 1 is level I. So we need to give them 1s in the column corresponding to alpha I. And for factor 2, since it's 1, we don't need to give them anything. And lastly, for these ones, their factor 1 is level I, so we need to give them 1s in the column corresponding to level I, and also 1s in the column corresponding to level j in factor 2. So it's still a binary design matrix, and for each row, you fill it out, or each block of rows corresponding to the same level I and j. For that block of rows, you just give them the same rows with zeros in everywhere, and 1s in the columns in corresponding to the levels of these observations. So that's what we'll do. So you can see that it's very easy to use programming to construct this design matrix, and then you're done. So then we will still finally have that block linear model, that matrix linear model, and we can still do the analysis we have talked about. And furthermore, given that we can do hierarchical Anova by having the table as we have, say, source of variation. We have factor 1 enters the model first, and factor 2 enters the model second, given factor 1. So we could do this. And what this is testing for is basically this hierarchical ANOVA, if we do this, is corresponding to testing whether gamma 2 to gamma j, they're all 0. Is corresponding to that. Answering this test, for this test, answering making decision for this test. And this can be done also by wall test, right? You're just testing a subvector of your beta vector, whether it's there or not, or likelihood ratio test. So these two things are still applicable. But the hierarchical ANOVA, if you do that in R, it will be something you get here. So still, the R command for doing this is this summary ln y tilde factor 1 plus factor 2. So as we said last time, the order you input those two factors will determine how the hierarchical ANOVA table look like. And the second one you input, or the last one you input, will be the one you use for the test. Okay, so just we can stop here for the hierarchical ANOVA and some other terminology to introduce for two-way ANOVA. So one is what we call the growth effect. So just some terminology to be good to know. So the growth effect is just the effect of one factor by having it as the only predictor in the linear model. Okay, growth effect of factor 2. Maybe I put it here. Factor 2 is just one-way ANOVA with factor 2 only. And we also have another term called a net effect of factor 2 given factor 1. Okay, so this is what can be addressed by the hierarchical ANOVA. So these are the two terms, which is this one corresponds to just one predictor model. This is multiple predictor model, and this factor is only one of the predictors. But when we say this, essentially we treat the factor 2, even though we treat it as one factor, but in effect, if you look at the linear model, you know that factor 2 essentially corresponds to capital J minus 1 binary predictors. So it's that accumulative or joint effect of those J minus 1 binary predictors. Okay, so that's the two-way ANOVA without interaction effects. Now let's add interaction effects. So with interaction effects between factors 1 and 2, how are we going to change the model? So which means that now the expectation of my observation is not just an additive effect of factor 1 and 2, but we need to consider their interaction. But how do they interact? That's a little tricky because here the two factors, their levels are non-numerical. We cannot assume it's a product or something. So we need to give them additional set of parameters to capture those interactions. So to change this, we basically need to change the systematic structure, which is, if you recall, is expectation of yijk. And we give it a notation mu ij, right? K is just the kth observation in that level ij. Previously, we write this as mu plus alpha I plus gamma j. But now we need to give it another term for the interaction. Okay, maybe we can call that, I'm giving another notation, eta ij. So this eta has two indices, I and j, means that it's the interaction between level I factor 1 and level j factor 2. Okay, so with this systematic structure, also to consider for identifiability, I need to set several of them to be 0. I will set alpha 1 to be 0 as we did, gamma 1 to be 0 as we did, and furthermore, for those etas, I need to set many of them to be 0. So that means I need to set eta whenever level I is 1, I need to set to be 0. So eta 1, 1 to eta 1 j, they need to be 0. And also, whenever the factor j is 1, I need to set it to 0. So I need to set, let's say, eta 2, 1 to eta I1. I need to set all of them to be 0. So in other words, whenever I is 1, eta ij is 0. Whenever j is 1, eta ij is 0. So that basically level I and level 1 factor 1 has no effect. Level j factor level 1 factor 2 has no effect. So I'm going to be consistent with that. So then you see how many parameters do I have? Let's do a count, okay? So the parameters for this two-way ANOVA with interaction, it becomes a lot of parameters. Mu will be here. Alpha 2 to alpha I will be here. So it's 1 parameter, I minus 1 parameter. Gamma 2 to gamma j will be here, j minus 1 parameters. And finally, I would have the eta. Okay, so I would have eta 2 going to eta ij. And I would have I minus 1 times j minus 1 parameters here. I think it's I minus 1 times j plus j minus 1. Is that right? Yeah, I think so. So then I can take the sum over other things. And I think what I will get is that this, putting them together, I call it beta, it will be equal to I j dimensional, I times j dimensional. Yeah, that's the number of parameters I will get for this two-way ANOVA with interaction effects. So let's imagine if your factor 1 has 3 levels, factor 2 has 4 levels. In total, the model parameters will have 12 dimensions. Okay, so given that you could do, in this model, often you can say if you write R as this, say summary, LM, Y regress on factor 1 plus factor 2 plus factor 1 times factor 2. That's the command. If you do that, then it means you put the interaction the last in your model. And then if you do hierarchical ANOVA, what you will get is you will have factor 1 first, and you will have factor 2 conditional on factor 1. And then finally, you'll have factor 1 times factor 2, the interaction, conditioning on factor 1 plus factor 2. So you have that. So then, as I said, in hierarchical ANOVA, you always concern the last row, the effect of this. So the F test will tell you whether this interaction gives you additional benefit given factor 1 and factor 2 are there. So if you are not going to reject this F test, it means that your inclusion of the interaction effect does not seem to change the model fitting too much. So in that case, you may want to drop the interaction because that can significantly reduce the number of parameters in your model. Okay, so the design matrix will be filled out accordingly. So I'm not going to do that, but you can think of it how to do it yourself. So basically, whenever an observation is in a level other than 1 in factor 1, you need to give it 1 in this alpha column. You also need to give it 1s in the eta columns where the factor 1 has level I. So you need to have more 1s in that row. And so that applies to factor 2 as well. So whenever you have observation, you just check its level in factor 1, its level in factor 2, and you fill in the corresponding columns with 1s in the design matrix. Okay, so that's two-way ANOVA. Finally, we will conclude this lecture by talking about analysis of covariance. I think some people call this ANCOVA. So what is analysis of covariance? So it's actually, don't be confused by the name. It's actually, you have both categorical predictors, factors, as well as numerical predictors in the same linear model. Okay, so a linear model with categorical and numerical predictors. That's the case we face in many applications. Not all predictors are numerical and not all of them are categorical. So for this, let's just make it simpler. So let's say that we have X as a numerical predictor. Okay, so for each observation I, we have a value xi. And we have another factor with I levels. Okay, a factor with I levels. That's our model. And still, ni observation in level I. And our sample size n is still the summation of ni, I from 1 to capital I. So then the systematic structure is just, okay, so basically we have this thing. So we need to have 2 indices. So one is for the level, one is the jth observation in the level. Maybe let's look at the random structure first before filling out the systematic structure. So we need Yij. Maybe I'll put it here. Yij is the jth observation in level I. But here, not all the Yij share the same mean. This is unlike one-way ANOVA. The reason is that each Yij has its corresponding Xij, which is this observation's value in that numerical predictor. So that's why here the systematic structure, we need to give each expectation of Yij a different mean. So the mean will be mu ij, and it will be an additive effect of the factor and the numerical predictor. So still an intercept, the effect of the factor at level I, and the effect of the numerical predictor x, beta xij. So just as in our linear model, we just give this numerical predictor a common slope, which means that the slope does not change with the level and the slope doesn't change with observation. It's just a common beta. But this observation J in level I has its specific numerical predictor value. We call it Xij. That's why here we have mu ij instead of mu I. If you recall, in the one-way ANOVA, each yij, so for different j's, they share the same mean. We call mu I, because in that case, the mean is just determined by level I. But here, we have the mean also affected by the numerical predictor xij. So then the random structure is yij following Gaussian with mean mu ij and common variance sigma square. Okay, so let's stop here, and you can think about how the covariance matrix, how the design matrix will look like for this ANCOVA model, and we will come back to this next time on Tuesday. So see you on Tuesday. And just as I did for my other class, some students prefer to stay in the Zoom for some discussion, after class discussion without my presence. So if that's something you want to do here, I can stop the sharing and I can leave the Zoom and leave you guys for discussion. Please just let me know. Okay. So anyone who wants to volunteer to stay